Welcome to another problem session. So this particular problem comes to us from this book, Klepner and Kolenko. It's a little tricky problem, but not that difficult. It just I would say it's on the difficult side, but fairly fairly accessible. Okay. So let's look at the situation more closely, and then once you look at it closely, you'll know this problem can be solved from what we have been talking about. So remember, problem solution, when you read the problem, okay, so first thing to think about is energy conservation. Then think momentum conservation or angular momentum. We haven't done angular momentum yet, but we're going to be doing that. And then the next one is next one is going to be your F equals ma, force conservation. When you think about energy, you include the work part, the power part. Okay, so those things come first, and then these guys come, and then this guy comes, and sometimes all three have to be used. All right, and makes the problem hard. All right, so let's now read the problem. So you have a hopper. Hopper is basically a funnel, and sand will just kind of fall from the bottom of the funnel. So you can say, hey, here is a hopper, and I fill with sand, and maybe you have a little valve, and you can turn it, and then sand will start to fall. All right, so that's the hopper, and since the sand will fall at a constant rate in terms of mass, and they didn't give you a value or anything, just some dm over dt. So you can say, well, let's start dm over dt. I want to call it alpha or something like that. So if I want to know how much sand going to drop in time delta t, in time delta t, as for example, from t to t plus delta t, delta m will be just alpha delta t, which is dm over dt delta t. It's kind of like that. Okay, so we understand how to take care of the mass part in a time duration. Recall from the last video, several videos we've been doing, we're always thinking in terms of time. What happens now and what happens a little bit later. All right, so we'll focus it between time t and t plus delta t. So we're going to pick a random time t to actually focus it. So some random time t. So this is random time t. You have a belt, conveyor belt, and this is a roller, and there is a motor here which kind of rotates, and the roller will rotate, and there is a friction here, so there is some kind of frictional force, and it has to be static friction to roll it, right? And the belt rides on it, so that's the force that's supplying, and the belt is moving at speed v, constant speed. Okay, so this is constant, and then of course the belt over there will be another roller, so it will wrap around there, and then is going to return. Meanwhile, the sand will start to fall on it, right? So we want to find out the power needed to drive the belt. So this is the force, and this is the velocity. So force, static force is that way, and the velocity is that way. So what we want, power at instant t, is going to be the force times V. Now we have to figure out how to get the force. Well, what is this force supposed to do? It's supposed to look at the change in the momentum, right? Force is dp dt, which is one dimensional, so we don't have to write x and x and things like that. So it's a one dimensional, same direction, not flipping back and forth, same direction. And same direction means just ignore the subscript, okay? Ignore x subscript. Now if it's not necessary, why put it, all right? So that's the case. So we have to figure out how much momentum it needs to account for, how much change in momentum it needs to account for in time delta t. So if I look at the t to t plus delta t, the new mass comes in, its velocity of change. So what happens here, delta amount of sand comes in at v equal to 0, its velocity increases to v. So that's what's happening in that little time that we're looking at. It's going to have to. So and if you look at this, all the dt's, so it's all these d's. So amount of momentum that must this F must be responsible, the rate at which momentum is changing is so dp will just amount of mass and v minus same amount of mass times 0, so dm times v. V is constant, so if I put this in here, the force turns out to be dm over dt times v. So now I can put over here, so dm over dt v times v is dm over dt v square. So that's A. That's the argument for A. The belt must be, is the motor that's moving the belt. Okay. Now, part B says compare this power. So if you want to say energy supplied by motor, which is putting in this much power, in delta t amount of time, this is the delta t amount of time, will be just pt delta t. So this is the amount of energy. All right. And of course, if you are going to do it for a large amount of time, then the E from some initial to final time, it will be time initial to time final, P of t dt. So you have to do those integrals. That's not a question, is not asking for that. So just aside, something that you should keep in mind in case it shows up somewhere. All right, so the B, to answer B, let's, it says, rate of change of kinetic energy of the sand. Well, how it looked like we already found this is the rate of, energy supplied by the motor. Should be the same. I mean, one might think that, well, what's overall happening? The sand just, its energy goes up, right? Its energy goes up. So because sand's energy goes up, the amount of energy that goes up must equal to the amount of energy that the motor is supplying. Let's see, that's the one you have to check, right? Is that really true? And so if you look at it, over here, over here we looked at the momentum. So looking at the kinetic energy of sand is very so so at t2 delta t plus delta t amount of time, what's going to happen in this time? So delta ke, just like this guy, will be just delta m, half delta m v square minus half delta m 0. So this is half delta m v square. So if I rate at which energy of the sand is changing, rate of change of kinetic energy of sand, just divide by delta t. This is the amount of time it took to change this much. Okay, so it's going to be half dm dt v square. That one is dm dt v square, and this is only half as much. So our intuition, we just use the regular intuition. You kind of miss something. That's not the only place the energy is going in. Just increasing the kinetic energy. What's also happening is there is actually, when the sand comes in, it doesn't just become V right away. It slides on the belt, and while sliding, it has some acceleration and some frictional force, and then that surface will actually heat up with time, and there's a dissipation of energy. So it's actually dissipation energy. So what's happening is, so the question is, where is the rest of the energy? Motor spent that much energy. This energy, they ended up in the kinetic energy of the sand. So where is the rest of the energy? That is the hard part. So let's look at the one of the particles. Let's call it delta m. So you have a delta m, and say at time t it's over here, and this is time t plus delta t, and so over here the v is equal to 0. It just came in, and over here it's going to be the v equals to v. Okay, so it's moving here, and we can say, well, how much distance did it go? Let's call it distance delta x direction. It went delta x. Now you can see the velocity increased that way, so there must have been acceleration that way. So what's the acceleration? Where acceleration can be, you can say v minus 0 over delta t. You can say v minus 0 over delta t. That's the amount of acceleration that it had. And it was same as there is some frictional force here, right? Frictional force, which is trying to slide it. Okay, so you have a frictional force. So this is the same thing, frictional force over delta m. This is delta m. So you can write either way. So those are some of the things you can write down, but how does it help? Well, if this frictional force is going to do work, then the work done by the frictional force, our motor has to work against this frictional force. It has to kind of supply the energy that the motor, that the friction force will do the work. Okay, so this work will be just F times delta x. And if you look at over here, you have it, F is, well, assuming the A is constant, we can actually relate to the delta X. We can find what the delta X is, okay? So say A constant, we just assume that, of course, it will not necessarily be constant, but you can assume this constant for doing the problem. So you have a V0, and you have a V equals to V, and this is delta X, and some constant A. Wait, this is very easy to do. 2A delta X is going to be V square. Just from like a chapter 1 or something. So we can get delta X written as a V square, or F in terms of A. So F A times delta M for F, and the delta X is V square over 2A. So A got cancelled out, and this whole thing happened half delta M V square. And this work was done in time amount delta T. So the rate of the work is W done about delta T. And so this is half dm dt V square. So whenever I got dm dt like this, I just changed it to dm over dt. That's all I did. And so now we see that this exactly what we needed on top of the kinetic energy to get the total energy this. So turns out what the motor is doing in this problem, very interestingly, motor is doing this problem is there's a work by motor in time delta T. So this is the power of the motor. This equal to change in kinetic energy of sand in that amount of time plus work by friction in same amount of time delta T. So this actually motor is doing some dissipative work, and then to bring the sand particle from 0 to the V, there is some amount of work has to be done. All right. Now this is a pretty interesting problem to me. I just can be very confusing when you're learning for the first time. You may have to kind of go over this solution one more time and maybe convince yourself. Maybe you have some other way of handling this problem also. So maybe you discover some new solution to this problem. Okay, that will be it for today. I'm going to just request that you subscribe to this channel. Looks like this channel is growing pretty well right now. Steadily, few of you come every day and subscribe. Tell friends if you find this kind of problem discussion, etc., useful, and maybe your teacher, etc. I'll attempt posting more regularly, like regularly once a day or something like that, and hopefully I'll get time to do that. Sometimes I get busy with the other things and then it's not possible to post it, but I try, and hopefully it will be helpful to you. Okay, with that, take care and bye.